Continuing with the unsymmetrical fault analysis on power system, today's session we will look into the line-to-line fault occurs on unloaded generator. Here I will consider a generator, unloaded generator, in which there is a fault is occurring between line B and C. Just I have shown the representation of a three-phase alternator which is operating under no load condition. In that case, IA is equal to 0, IB is equal to 0 and IC is equal to 0 in this condition. And at the same time, the generated voltages are EA, EB and EC in all the three phases. They are displaced 120 degree and the terminal voltage VA, VB, VC are also equal because it is operating under no load condition. Therefore, EA is equal to VA, EB is equal to VB, EC is equal to VC. Now, there is a fault is occurring between B and C. The fault is occurring between B and C. There is a fault is occurring between B and C. When there is a fault is occurring between B and C, what are the prevailing boundary conditions they are prevailing? That we have to look into. That is, the first boundary condition what I am getting here is the terminal volt, that is the current in the phase A is 0, but it is not involved in any fault. Therefore, it is operating under no load condition. Therefore, IA is equal to 0. At the same time, if you look into the voltage, the terminal voltage of phase B and C, they are all equal. Therefore, that second terminal condition, what I am getting is VB is equal to VC. VB is equal to VC. And ultimately, the fault current is either it is IB or it may be minus IC. It is IB or minus IC. Therefore, I will write the boundary condition here. That is the first one is what I am writing here is the boundary condition is the current IA is equal to 0. I is equal to 0. Then the second boundary condition what I am getting is VB is equal to VC. VB is equal to VC. Then the other condition is if you are looking to here the current IB and IC, they are both equal and opposite. Therefore, I will put IB is equal to minus IC. These are the conditions what I am getting from the line-to-line fault. Then if you are looking to the voltage equation or sequence voltage equation, that is VA naught in terms of VA, VB, VC, or it is 1 by 3 VA plus VB plus VC. I will keep as it is. Then VA1 is equal to 1 by 3 VA, that is AVB plus A square VC. Then VA2 is 1 by 3 VA plus A square VB plus A VC. Then we know the condition that VB is equal to VC. Just I am replacing here it is VB, that is it is 1 by 3, that is VA, that is VB, A plus A square, that is bracket I will complete, second bracket. Then here also what I am getting is 1 by 3 VA plus, once again VC is replaced by VB, VC is replaced by this VC and this VC are replaced by VB. Therefore, what I am getting here also VB I am taking common. Once again in the bracket what I am getting here is also A plus A square. A plus A square. If you are observing the value of VA1 and the VA2, they have got a same value. Therefore, the first conclusion from this what I am getting here is VA1 is equal to VA2. That is, the positive sequence terminal voltage VA1 is equal to negative sequence voltage VA2. That is the first, the condition, that is the first, the relations what I am getting from this the condition, that is VB is equal to VC. Then if you are looking into the second, the sequence currents that I am looking to, that is sequence current. Sequence current, just you have to look into the sequence currents now. Just I will change the each color in. Okay. Now I have got the relation IA naught. IA naught is equal to 1 by 3 IA plus IB plus IC. Then if you are putting the value, the condition, the IA is 0, then IB is equal to minus IC. Therefore, what I am getting is 1 by 3 IA plus IB. Okay, thus I am putting as a minus IB. IB is equal to minus IC. Therefore, IC is equal to minus IB. That is, these two get, that is IB is minus IC. Then this is 0, IB minus IC is 0, whereas I is also 0, therefore there is no zero sequence current. It is quite evident also from the diagram itself. That is, in the case of thus, in the fault, as such the fault is not involved with any of the ground, that is, it is not involved with the ground, therefore the zero sequence current is 0. Then if you are looking to the positive and negative sequence current, then I look for the current IA1. IA1 is 1 by 3, it is IA plus AIB, it is A square IC. Once again, if you are looking to here, 1 by 3, IA is 0, then IB can be replaced by minus IC. Therefore, what I am getting here is, it is A square minus A into IC. Just you have to put the value of IB, instead of IB, I am putting minus IC. Therefore, it is minus AIC. It is A square IC. Therefore, A square minus AIC, what I am getting is for IA1. Then the next one is the IA2. IA2 is 1 by 3, it is IA plus, it is A square IB plus AIC. Therefore, once again, if you are putting the value here, it is 1 by 3, IA is 0, here IB is replaced by minus IC, then what I am getting here is A minus A square into IC, that is IA2. Therefore, what I am getting into, that is the value of IA1 as A square minus A into IC, whereas the IA2 from this relation, what I am getting here is, it is of course it is 1 by 3, it is A minus A square. Therefore, I am taking here minus outside here, it is also I am getting A square minus A into IC. Means from these two relations, what I am getting ultimately is IA1 is equal to minus IA2. That is another condition we are getting. The same thing I am showing here with a clear cut the PPT presentation here. That is, this is how we have to establish a relation between IA1 and IA2 and VA1 and VA2. These are the two important the relations that were established from the sequence voltage and sequence current. Okay, that I will show you here. that is okay. That is the line to line fault is occurring here. Then the boundary conditions they are that is defined, that is VB is equal to VC, VB is equal to VC, then IA is equal to 0, then IB is equal to minus IC, IB is equal to minus IC. These are the boundary conditions for line to line fault. Then if we are putting the VB is equal to VC in the sequence voltages, that is VA0, VA1, VA2, that is 1 by 3, 1, 1, 1, 1A square, 1A square A, then what I am getting here is, because VB is equal to VC, therefore this VC, actually here it is a VC, VC is replaced by VB because it is VB is equal to VC. Then if you are realizing this, then what I am getting is condition is that what I derived with the writing the equation clearly, I derived that is VA1 is equal to VA2. If you are using this also, you are getting VA1 is equal to VA2. Okay. Now you go for the what is the current relations. We know that IB is equal to minus IC, IB is equal to minus IC, and IA is equal to 0. These are the boundary conditions I have got. Then same boundary conditions if you are putting in the sequence currents, that is IA0, IA1 and IA2, then what I am getting is IA is 0. Instead of IB, I am replacing by minus IC because my IB is equal to minus IC. IB is equal to minus IC. Therefore, here VA0 we are getting 0 because your IA0 we are getting a 0 here because it is IA0 is equal to 1 by 3, 0 minus IC plus IC, that is equal to 0. Therefore, VA0 what we are getting is 0. Therefore, IA0 is equal to 0 we are getting, and the second conditions what I am getting here is, it is A1, IA1 is equal to minus IA2. Here it is a minus IA2. It is a minus IA2. It is a minus IA2 here. Okay. Just I will show you that is better. That is space is required here. Okay. Okay. That is IA1 is equal to minus IA2. Okay. Then we are interested in what are the sequence voltages, because we know the conditions IA1 is equal to minus IA2. Then we have to get what is the VA2 is equal to VA1. That condition we are derived from the voltage sequence voltages, that is VA1 is equal to VA2. Just I am putting VA2 is equal to IA1Z2, because can look into here in the right hand side. See here, VA is equal to 0 because IA0 is equal to 0, and VA1 is equal to EA minus IA1Z1, that is as it is, whereas the VA2 is, that is IA2Z2, actually IA2Z2, but IA2 is minus IA1, minus of minus plus, therefore it is plus IA1Z2. Therefore the same thing I am putting here, that is IA1Z2 is equal to EA minus IA1Z2. Here there is only one unknown quantity, that is IA1. Therefore if you are taking IA1 common, that is one side, that is coefficient of IA1 you can take one side, and then if you are taking common IA1, then what is left out is Z1 plus Z2, that is equal to EA. Therefore we are getting IA. Once we know the value of IA1, IA2 is equal to minus IA1, then IA0 is 0. Then you can calculate the what is the fault current, that is IB and IC. That I am showing here, that is the fault current is, it is IA0, A square IA1 plus A IA2. IA is equal to 0, then it is IA1 is equal to minus IA2. Therefore it is becomes minus A IA1. This particular term is become minus A IA1. Therefore it is IA1 I am taking common, therefore what is left out, A square minus A square minus A. Therefore putting the value of IA1 from this equation, what I am getting here is A square minus A divided by EA Z1 plus Z. Z1 plus Z. That is, it is IB or it is minus S. That is one and the same. A square minus A divided EA divided by Z1 plus Z2. This is the fault current. How we have to calculate? Just you have to put the boundary conditions in the sequence currents and the sequence voltages and the sequence network voltages in terms of its impedance and IA1 you have to substitute properly the derived relations here. VA1 is equal to VA2 and IA1 is equal to minus IA2. Then we are arrived at the fault current of IB. Then one important relation what I am getting here is the VA0 is equal to 0. However, VA1 is equal to VA2 I am getting. Means VA0 is 0, means there is no existence of zero sequence network, and the VA1 is equal to VA2 means the positive sequence network is connected in parallel with the negative sequence network. That I am showing here. These are the derived conditions, that is the IA0 is equal to 0 you are derived, IA1 is equal to minus IA2 and here also, and VA2 is equal to VA1, that also we are derived, and VA0 we are getting 0 because IA0 is 0, therefore VA0 is 0, therefore IA1 what I am getting is A divided by Z1 plus Z2. Ultimately the fault current what I am getting here is A square minus A into EA divided by Z1 plus Z2. And as far as the sequence networks are concerned here, they are connected in parallel. They are connected in parallel. This is a positive sequence network, this is a negative sequence network. These two are connected in parallel. These two are connected. This is how we have to analyze the line to line fault on the unloaded generator.